All right, let's start off with our redox review. What I'm going to tell you is a few things that will help you through most of it. So first, for hydrogen, okay? Now, when in a compound, okay, hydrogen is always +1, except, of course, there's an except, right? So let's go to the periodic table and see why. So here's hydrogen. You see it has two options, +1, -1, but it is in reality almost all the time the positive one, except for when we have metals. Because if you start scanning all the metals, right, which are on the left side, all this stuff right here and here and here and here and here, all these groups, they all have positive and never have a negative option. So if I go back here, hydrogen, when it's in a compound, hydrogen is always +1, except when hydrogen bonds to a metal. Then it's -1, okay? Now, what about when hydrogen is not in a compound? So all elements without a charge that are only bonded to themselves have an oxidation state of 0. Okay, so what do I mean by that? All right, first let me change the color here. All right, so what exactly do I mean by that? All right, I mean if it is just singular Na, if it is O2, if it is S8, those all have an oxidation state of 0. What do I mean if it had a charge? Well, let's look at an example. So that would be if it was Na. And how would I know it had a charge? Bam, up there. S. Bam, up there. Then the oxidation state is not 0. The oxidation state is what the charge is. Okay. All right. And then in general, in any compound, so I'll just write NaCl. In any compound, the first element will have a positive oxidation state, and the last element will have a negative oxidation state. Okay. However, remember this rule about hydrogen, because that can override that. All right, so let's look at what I mean. All right, so here's the first one. And I'm finding the oxidation state of hydrogen. Okay, hydrogen is combined with K in this case. So let's look at the periodic table. Where's K? Right here. K is a metal. So what did I tell you? When hydrogen is combined with a metal, its oxidation state, hydrogen's oxidation state, will always be what? Oops. Do you remember? -1. So in this case, the K is +1 and the H is -1. Okay, and there's one of each of them, right? So a positive one and a -1, well, that makes sense. That gives me 0, and there's no charge up there. All right, so let's look at this one. All right, I have NH3. So H is with nitrogen. So let's go to the periodic table. Here's nitrogen, not a metal. So that means what is hydrogen's oxidation state? +1. Why does it work out? Well, there's 3 hydrogens. So a +1, a +1, okay. So +1, a +1, a +1. Right? 3 hydrogens that have +1. Each one has a +1, so that would be +3 altogether, right? And what would nitrogen be? Well, if hydrogen is adds up to +3, then nitrogen would have to be -3 because overall there's no charge. And then we look here, yeah, nitrogen, -3 is a possibility. But I didn't have to find nitrogen in this case. I'm just backtracking it for you because look, down here, we just did it ahead. Here's nitrogen. So I just found that one, right? What was it? -3. All right, so I just did that one. All right, so let's go back up here. Let's look at this one. So I have H2. Do I see a charge? No, I do not. So what is the oxidation state? Do you remember when it's an element only bonded to itself? No charge, 0. All right, so let's look at this one, okay? I have hydrogen. Check. Is it just hydrogen bonded to one metal? No, it is not. So what is its oxidation state? +1. All right, what is the oxidation state of oxygen? All right, I'm going to look and I'm going to do the easy one first because why make your life harder? Look at this one right here, this last one. Oxygen, just itself. Oxygen bonded to itself with no charge, 0. Bam. Okay. Now let's look at this one. These next two, both are oxygen with hydrogen, but different amounts of hydrogen. So it's obviously going to be different. So for these, I'm going to show you how we write equations. So 2 H's plus 1 O is going to give me 0. Why do I make it equal to 0? Because I look up here and I don't see a charge written. So that means it has to equal 0. All right. Then I solve. And in this set of questions, I'm solving for oxygen. So I put in hydrogen's value and I solve for oxygen. So that's going to be +2. So in order to get rid of +2, I do -2 on the other side, on both sides. So I get -2. So this one is -2. This one should not give me the same answer because it is a completely different formula with the same element. So odds are it's not going to be the same. So 2 H's plus 2 O's is 0 again, right? No charge written up there. I'm solving for oxygen, so I use hydrogen to help me. And I'm going to solve it the same way. So that's a +2, right? 2 times +1. So in order to get rid of that, I do -2 for both sides. So I get 2O equal -2. Divide both sides by 2. And in this case, O is going to equal -1. So it is different, which is what I suspect, because with a different formula, I would not suspect that I would get the same answer. This one, OF2. Okay, so I have to be careful for this one, all right? Let me write the formula first. All right, I have one O and 2 F's. I add them together, I get 0, right? No charge. I'm solving for oxygen, right? So that means I'm going to leave oxygen alone and plug in the value for fluorine. So let's go to the reference table. Fluorine right here, -1. So I plug that in, -1 equals 0, right? O, so 2 times -1 is -2. So to get rid of it, I add 2 to both sides. Well, look at that. So that's different. Oxygen is +2 in this one. All right. So again, why can that happen? See how it says selected oxidation states? So some of these elements have other oxidation states. Well, they all have 0, and 0 is not written anywhere. So obviously there are more. But other elements have more uncommon oxidation states that aren't in the list. So just because you get an answer that's not on the table doesn't mean it's wrong. Okay. All right, this next part, I'm solving for what element this time? Chlorine. So that means I have to use whatever other element is there to solve for chlorine. So in this one, I start with my equation, Ca plus 2Cl's equals 0, right? I'm using the other element to solve for chlorine, so I have to look up calcium, and it is +2. So positive 2 plus 2 chlorine equals 0. All right, then you solve for it. What do you get? Hopefully you get the same answer I do, which is negative 1. You have to be able, absolutely have to be able to solve an equation like this. All right, this one is easy peasy as one singular element of chlorine, and then look, there's a charge. So the oxidation state is simply what the charge is, negative 1. Whew, okay, this one looks a little bit more complicated. So let's do this one kind of step by step. Are you ready? I've got 1 Al plus, I've got 1 Cl in the parentheses times a 3 outside. So that gives me 3 Cls, right? Plus I've got 2 oxygens inside the parentheses plus, times 3 outside. That gives me 6 oxygens, and it has no overall charge, so it equals 0. I'm solving for chlorine, so I have to use aluminum and oxygen. So aluminum, positive 3, oxygen, minus 2. So let's plug those in. So positive 3 plus 3 chlorine plus 6 times negative 2 equals 0. All right, so that's just 3 plus 3Cl plus negative 12 equals 0. Combine those like terms. I get 3Cl plus negative 9 equals 0. Add 9 to both sides. 3Cl equals 9. Divide both sides by 3. Cl equals 3, or Cl equals, because we have to put the sign, right? Positive 3. So this one is positive 3. And if we look at the list for Cl, that again is not in the list, but I can check my math. If I did it right, trust your work. All right. This next one is really easy. So I'm solving for nitrogen for this one. Remember, we already did the first one. And when I solve for nitrogen, I've got 1 nitrogen and 1 oxygen, and it has to add up to 0. So if I look at oxygen, it's negative 2. So if oxygen is negative 2, what does nitrogen have to be? Positive 2, right? Okay, this one, we will set this one up. Ready? So I have nitrogen, nitrogen plus 3 oxygen, but it does not equal 0. What does it equal? Negative 1. So be careful. Here's an example with that, right? Pay attention. So I'm solving for nitrogen, so I have to use oxygen to help me do it, right? So 3 times negative 2 equals negative 1. Now, if it doesn't tell you which element, you're finding, and you have to find all of them, then use the ones on the periodic table that only have 1 charge, like this one and this one and this one, to help you solve for ones that have a list, like this one. Okay. So now what do I have? N plus negative 6 equals negative 1. Add 6 to both sides. So N is positive 5. So positive 5. Let's check the periodic table. And look, that one is an option. Like nitrogen has so many. So that one is an option. So there you go. That's how you do oxidation states, right? Don't forget about this hydrogen rule, right? That's important. General rule right here, right? The zeros, okay? And don't forget how to set up and solve equations. Pay attention to charges, right? There are lots of pieces to this, and you really need to be able to do this in order to do some other stuff in this unit. All right, there's the first part. All right, now we're going to do this next question. So during a laboratory activity, appropriate safety equipment is used and safety procedures are followed. A student tests samples of 4 different metals using 0.20 molar aqueous metal ion solutions of the same 4 metals. The student uses a 24-well plate as the reaction container for the different metal and solution combinations. Before placing a metal strip in each solution, the student cleans the surface of the metal strip with sandpaper. The 24-well plate diagram shows the setup and results of the investigation. In each vertical column, the metal strips are all the same metal. For each horizontal row, all the solutions contain the same type of metal ion. So let's look at the diagram and make sure we understand what that means. So that means here's the metal strip. So magnesium is the metal strip for all of these. Zinc is the metal strip for all of these. Okay. And then likewise, when we are looking at the columns, the rows going across, magnesium is in the solution, in the aqueous solution for all of these going across, right? And so on. It's important that we stop for a moment and look at the key. Like if they give you a diagram, you got to make sure you understand it, right? So this says a metal strip with no change. So do you see, here's an example right here. So when there's no change, what does that mean? That means there was no reaction. Oops, spelled reaction wrong, right? If the metal strip appears dark in the solution, there was a reaction, right? What did we use in class when we were talking about this? We used table J, right? So when a strong metal, like lithium is the strongest, right? When a strong metal was on a metal strip, annoyed, bounded, made to like not be able to move, it would kick out any metal below it and take its place so that it could be in the solution and move around. So the ones in the solution, so over here, the ones in the solution, they're free to move and 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 move. The metal strips, they're stuck on this plate. And if it's a strong metal that is stuck on the plate, it is miserable and it wants to get out. Okay? So now let's look at the questions. State why the student was instructed to clean the surface of the metal strips with sandpaper before placing each strip into an aqueous metal ion solution. Okay, well, metals are going to react with air and oxidize, so I want to clean that oxidation off. So I want to remove any oxidation. What else could I say? Increase the surface area of the metal that will react. Okay. I could say remove any contamination or rust. All right. Those are some options. Okay. I want it to react better. Now it says write a balanced half reaction equation for the reduction of the copper ions. So let's see. Do you remember this? I gave you two phrases. Leo says Gur, right? And I said oil rig, right? Whichever one you like better. But to do this, I just need a quick number line. 0 going this is just so I know where 0 is. If I go this way, I'm losing electrons. Okay, that would be also oil. This way, I'm gaining electrons. All right. So now it says I'm reducing the copper ion. So that means they're gaining electrons, right? Reduction is gain, gaining electrons, reduction. When you gain electrons, you see how I put this arrow this way? That means the electrons are on that side of the equation. All right. So I can set this up. I'm not going to be complete, but what I can set it up as, I know the symbol for copper is Cu, right? I know in order to be reduced, it has to gain electrons. All right. And then I have to have copper on the other side because I have to have conservation of mass. Okay. So now I'm going to look at what I have up here. And I see that it says I have a copper 2 ion. And besides the copper 2 ion, right? So that's right here. I have copper as a solid. So I'm going to go back to what I had here. All right. And I have copper as a solid and copper as a +2. So I have to think for a moment. In order to have a charge, I have to conserve charge, right? If this was positive on this side, so I just write it like this for a moment. If I put the positive on this side, would there be any way for me to make this side be positive? No, because my only other option is the copper with no charge. So that won't help me. So I need to start on this side. Okay, so copper plus 2. All right. And it's, I mean, that should be a superscript. So we'll just pretend that's a superscript. All right. And on this side, that's going to be, I don't have to write the solid, but I'm going to do this anyway, just so you can see which one I'm looking at. So that was the aqueous one, and that was the solid one. But now I have to think. I went from positive 2. So 1, 2. Right? There's positive 2, and I went to 0. How many electrons did I gain? Well, 2. I didn't just write electron. It's not like a default, okay? Now I make sure charge is balanced. So what do I have on this side? Positive 2 plus negative 2, that's 0. And I have 0 on this side. Voila, I'm finished. All right, next question. Compare the number of electrons lost by the magnesium placed in the zinc 2 plus aqueous solution to the number of electrons gained by the zinc 2 plus aqueous. Well, the number of electrons lost must be equal to the number of electrons gained, period. If it's 1 electron gained, 1 lost. 2 gained, 2 lost. 5 moles lost, 5 moles gained. 1.2 moles lost, 1.2 moles gained. Okay. Using the results of the student's investigation, state evidence that zinc metal is more active than copper metal. So I cannot talk about table J. I want to look at their evidence. So what do I see? Well, let's compare zinc and copper. So here is the copper piece. Here is the zinc piece. So if I look down copper's column, none of it reacted. But if I look down zinc's column, 2 of the zinc strips reacted. So 2 of the zinc strips reacted, but none of the copper strips reacted. This shows that copper is less active and zinc is more active. All right, so there we go. That is that question. Okay, for this next question, I'm going to model the strategy that I want you to employ most of the time in the exam. Look at all this reading. Skip, 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 go to the question. Now, this one says state. It's not a question word. Usually it's going to be, what or how. But here's the question word. State the change in oxidation number for oxygen during the electrolysis reaction represented by the equation. So in reality, I need to read none of that. How about stop confusing yourself? Don't read it if you don't need to. All I need to look at is this equation. So I need to figure out what the oxidation number. So it says the oxidation number for oxygen changes from blank to blank. So what has to go here was what oxygen was as a reactant, and what goes on this side is what it is as a product. Okay. So I'm going to do the product one first because that is easy peasy. Look at it. It is oxygen, gas, no charge. So I don't care that it's oxygen bonded to oxygen or bonded to oxygen. It's not bonded to anything else. It's just bonded to itself. When it's bonded to itself with no charge, it is going to be 0. All right. Now over here, I'm going to figure it out. So do you remember we learned about hydrogen, right? So 2 hydrogens plus 1 oxygen equals 0. I know that oxygen is not a metal, so that means hydrogen in this case must be plus 1, plus oxygen is 0. Oops, that was just a lowercase o. So that's plus 2, subtract 2 from both sides. Hopefully you realize this, it's negative 2, which should make sense, right? Why? Because 1 hydrogen plus 1, 2 hydrogens plus 2. Oxygen would have to be -2 in order to balance and get 0. All right, that is that question. Okay, are you ready? I am going to give you a strategy for this. So, we have the strategy, ignore the question, right? We have a lot of stuff. I see this diagram. What I'm going to do is label as much as I possibly can before I even look at the questions. It will make it easier. So I can see that the 2 metals I have are magnesium and copper, right? So I'm going to go to table J, and here's magnesium, and here's copper. So which one is higher? Magnesium. Okay, so that one always 100% of the time will be the negative electrode. So I know that this one is negative and this one is positive. This is a voltmeter, and it says it's a voltaic cell. So in a voltaic cell, the metal that is higher is the anode. Okay, so I'm going to go back here, and this is magnesium, so this is the anode, which means this is the cathode. Okay, then I'm going to remember this phrase. Remember, red cat, so, and an ox. I kind of only have to remember one of them. So that means at the cathode, I have reduction. At the anode, I have oxidation. All right, what else do I know about reduction? Reduction is gain of electrons, or rig, right? Anode, which is oxidation, is Leo, or oil, whichever one you want to remember, right? If something is gaining electrons, the Cu piece gets bigger, right? If the Cu piece gets bigger, that means more mass, more atoms, but less ions, okay? And magnesium is losing electrons. So the Mg piece gets smaller. It's losing, okay? Which means less mass, less atoms, more ions. Okay, that is most of what I should be thinking about. Then I'm also going to draw which way do electrons go. Well, let's see. Do you remember fat cat? Electrons go from anode to cathode. So anode over here. So electrons are going to go like this, right? And continue like this. Also, fat cat can help you remember that the cathode gets fat. That's why it gets bigger. All right, so fat cat can help you with 2 things. And then what goes in the salt bridge? Well, back and forth in the salt bridge would be the ions. So the electrons move through the wire and the ions move through the salt bridge. Okay, I think I have pretty much what I would want to label, so now go to the questions. Write a balanced equation for the half reaction that occurs in the copper half cell when the cell operates. Now, what I want you to see here is this. So do you see this? They already gave me a big chunk of the equation, so please don't make it harder. So what I'm going to do is just under here, it said copper, right? So I'm just going to write down what the copper part of this is so far. So Cu 2 plus aqueous, right, yields on the other side Cu as a solid. Okay, so that is just literally using what they gave me right here. But in order for it to be a half reaction, I need to put the correct number of electrons on the correct side of the equation. So here is where I told you having a quick number line, 0. When I move this way, that's Leo. Okay, and no, that is wrong. Ignore that for a moment. Okay, when I go this way, I'm losing. That is Leo. Whew, glad I caught myself there. Go this way. I was concentrating so hard on whether I was going to write Leo or oil that I wrote it the wrong way. So this is correct. So going from +2, so +2 is over here, going to 0. Right, so +2 to 0. I gain some electrons, right? I followed this arrow, and the electrons go on that side of the equation. How many did I gain? 2. So it should look like this. Cu 2 plus aqueous plus 2 electrons yields Cu as a solid. And balance the charges, double check. +2 minus 2 is 0, and it's 0 on that side. Perfect. Compare the number of electrons lost to the number of electrons gained during the reaction of the operating cell. So the number of electrons lost must be equal to the number of electrons gained. Identify the subatomic particles that flow through the wire. Oh, I already wrote them up there. What are they? Electrons. State the purpose of the salt bridge. Well, I drew some arrows, right? So allows ions to move back and forth to keep the cell neutral. Okay, keep it neutralized. Explain in terms of electrical energy how electrolysis differs from voltaic cell reactions. So in electrolysis, electrical energy is converted to chemical energy, but in a voltaic cell, chemical energy is converted to electrical energy. All right, so let me just there so we can actually see it. There we go. How does the concentration of copper 2 ions change as the cell operates? Ooh, I already wrote that down. What happens? The concentration of ions decreases. Okay, so let's move this over. Concentration of copper ions decreases. How does the number of copper atoms change? Okay, so the number of copper atoms increases, right? Because it's a fat cat, the cathode gets bigger. State in terms of the relative activity of metals why the reaction in this cell occurs. The reaction occurs because which one was more active? Magnesium is more active than copper. What would be needed to convert this into an electrolytic cell? A power source like a battery, right? Would be needed to convert it into an electrolytic cell. So do you see, although I didn't need all of the information I put in the diagram, it sure helped me answer these questions a lot faster, right? So do it. All right, we have one more question, and I am going to start with the same thing, right? So I know it's a voltaic cell, right? And I can see what elements I have. I have copper and I have chromium. So let's go to table J. All right, let's remove this so I'm not confused. All right, let me go back again. And what do I have? Copper and chromium. So let's go. Here's chromium and here's copper. So what I should remember is that the one that is higher will always be negative. The one that is lower will always be positive. So chromium is negative, copper is positive. In a voltaic cell, the higher one will be the anode. Okay, so now, which one was higher? This one. All right, so this is the anode, right? And then I'm going to remember a bunch of stuff about anodes. Anodes have oxidation occurring, right? Oil and Leo. In oxidation, we lose electrons, right? When we lose electrons, the piece gets smaller. When a piece gets smaller, it means there's less mass, less atoms. So what's happening? They're moving into the solution, so more ions. All right, now let's do something similar on this side. Okay, so on this side, this was lower. So the lower one is the cathode, right? The cathode, red cat, has reduction. Reduction means gain electrons, right? When you gain electrons, the piece gets bigger. When it gets bigger, that means more mass, more atoms, and less ions. So the ions come out of solution, right? And now we have atoms. So how do you remember that? Remember fat cat, the cathode gets bigger, right? Okay, now we just have a couple things to draw. Electrons move through the wire from anode to cathode. So this is electrons. I have to go from anode to cathode. And then in the salt bridge, we have ions moving in both directions, right? And then notice I do have this down here if I need it. This is a great start for any half reactions I have to write. Okay, so let's get started. Which metal is oxidized? Ooh, I'm really glad this question is here. Look at, when I write which metal is oxidized, I can only write something on this side of the equation. This is what happens after oxidation and reduction. So I only write it from the reactant side. So which metal is oxidized? Well, that's at the anode, and chromium looks like this, right? If it said which metal is reduced, right? Which metal is reduced? I would write this, Cr. With which metal is reduced? Cu2+. That's what I would have to write because that is what is on the reactant side. Label the anode and cathode. I did that. What moves through the wire? Electrons. From anode to cathode, right? Just as a note. Remember, fat cat, from anode to cathode. Draw an arrow. I did that already, so that was done. What moves through the salts bridge? Ions. What type of reaction occurs at the anode? Oxidation. At the cathode? Reduction. How does the mass of the copper electrode change as the cell operates? Well, I wrote it over here. The mass increases. How does the size of the chromium electrode change? The size decreases. It gets smaller. All right, now oxidation and reduction, half reactions. I got one more little thing I have to draw, right? Remember I told you number line, right? 0. Leo is this way, losing electrons or oil, right? And gaining electrons is this way. Okay. So now I'm going to use what is down here to help me. So oxidation, let's just start with the framework. Oxidation was happening with chromium, right? And chromium starts like this. 2Cr solid yields 2Cr 3 plus aqueous. All right, and I'll start the reduction. Reduction was occurring at the cathode, and that was with copper. And copper starts as 3Cu2+, and on the other side, it is 3Cu solid. All right, now, according to what I drew right up here, when something is oxidized, the electrons must go on the product side, this way. And when something is reduced, the electrons are gained, so they must go on the reactant side. All right, so that means I know for this one, I have to put the electrons over here. And for this one, I have to put the electrons on this side, right? So that diagram can help me with a lot. But I have to put the right number of electrons. Right now, it's a mess, okay? So if I just show you in terms of balancing charge, right? That's 0, 2 chromium with no charge. 2 times positive 3 is positive 6. And 1 electron only gives me negative 1. So that means this side currently has a positive 5 charge, and this side has a 0. Yeah, that can't be. So what do? I figure out when chromium went from 0 to plus 3, right? How many electrons did it lose? Well, 3, right? But there are 2 chromiums. So how am I going to write this completely? 2 chromium solid yields 2 chromium 3 plus aqueous plus 6 electrons. All right, let me just change this color so we can see this is the correct answer. This one in red. Now I have positive 6 and negative 6, which gives me 0. All right, so let's think about that as we're doing this one, right? So copper went from positive 2 to 0, right? So it gained 2 electrons, but there were 3 coppers. So how many did it gain altogether? 6. And we can check that. 3 times positive 2 is positive 6. 6 times negative 1 is negative 6. So positive 6 and negative 6 will give me 0 on the reactant side, and 3 times 0 is 0, and 0 on the product side. So there we go. There is the half reaction. And that is it. That is the whole review sheet.